I will link the full.
Okay, let me do a response to your response. Here we go.
Check it out. Yeah, I've got a feeling he's gonna add gravity into this at some point.
Am I going to add gravity into this? I suspect that I will. I'm trying very hard to remain open-minded and examining the evidence and taking it where it takes me. And wherever the evidence takes us, that's where we should go. That is my point. And I will begin deliberately from the point of view that we are questioning gravity. I'm aware of gravity, of the equations of gravity and how they work. I think you're probably aware of most of that as well. And yet you have chosen to say you think this relative density thing works without gravity. So I am trying very hard to make that work.
So for me, the explanation, they are not weightless at all. I know you use the quotation marks with your fingers, but they are not weightless at all. They still have full weight. The weight hasn't changed.
There are different definitions of weight. And so depending on which definition of weight you're using, you are either weightless at this point or you are not weightless at this point. Now this is extremely confusing. I thought that it would clear things up by calling that weight, but it seems like it's made it worse. So going forward, based on your feedback, I'm going to change weight to the word force. What I am describing is the net force acting on the object. When we see something hovering, that is zero net force. If that thing is accelerating downward, it is experiencing a downward net force. If it is moving upward, it will have an upward net force. Okay, and same thing side to side. If it's going to the side, we'll call that a sideways net force. Okay?
Imagine you have balls on the floor, like lots of small balls, all on the floor of the airplane. Okay, now imagine these balls are the air. Okay, so these balls represent the air. We'll pretend there's no balls above them for now, no air above it. And we'll pretend that air just goes in a downward vector for now, just to simplify things. So air just goes down for now, it doesn't go in all directions. Okay, now imagine you accelerate that floor down faster than what the balls fall. So the balls fall at a specific rate, and then you accelerate the floor down faster than what the balls are falling. Therefore, the balls are going to lag behind. So that means the air is going to lag behind. That means that you're going to end up with more dense above, towards the top of the plane, and less dense below. So, because the balls are not able to catch up with the floor. So they get lagged behind, because the floor is accelerating down faster than what the balls are falling. Again, the balls represent the air. So you end up with less dense below and more dense above.
Yes, absolutely. And there will be a density gradient caused by that. You'll get a more dense air at the top, less dense air at the bottom. Absolutely correct. Saw some people in the chat maybe criticizing you for that, but no, you're right insofar as that goes. I agree. You will get more dense air up, less dense air down if you're accelerating downward.
What do helium balloons do? They go to less dense. What did it do if it fell and it went to less dense? Now with the left and right thing, so basically what happened there is obviously the plane must be accelerating in a direction, and the air is shifting to where the people are shifting. So in this case, going to the left. So then you end up with more dense air, towards the left because it's shifting that way. Because of the acceleration, like in a car, the air will shift. So you end up with more dense one side and less dense the other side. So then the balloon ends up going to the less dense because it's less dense. So that's essentially what's happening there. It's still relative density.
The helium balloon is doing the opposite of what heavier than air things did. And you're just connecting the dots. This is a fair point. We agree that you will have more dense air at the top of the plane, if you're diving, if you're accelerating down harder than 9.8 meters per second squared. There's denser air at the top, less dense air at the bottom, and sure enough, the helium balloon goes down towards that less dense air. There's a correlation here. there is a correlation. The helium balloon is going where the less dense air goes. Right. That is a fair correlation. But let me ask, why? Your thoughts, as they were just expressed, sounds like you're saying the helium balloon naturally goes to less dense location. And so if the air is less dense down below, the helium balloon will be driven down. Why is the less dense air down below? The less dense air is down below because of the acceleration of the plane. And that's the point I've been trying to make, is that that the acceleration of the plane is causing denser things to go up and less dense things to go down. So the air itself, you can just set the helium balloon aside, the air itself has separated very slightly so that the more dense is up and the less dense is down, right? And that was caused by this accelerating aircraft.
Again, another way that we can prove this, if somebody had something like tungsten hexafluoride or sulfur hexafluoride, some kind of dense gas maybe that can go down in air, because more dense down, less dense up, even though gas still eventually goes in all directions and that. Obviously that depends on energy and a lot of things. But yeah, if we had something more dense than a helium balloon, more dense than helium, and we had an helium balloon in a container, and we poured this gas, this denser gas, towards the one side. Obviously, gas goes in all directions, but obviously, if it goes in all directions, obviously one of those directions is down too. So you could pour some of this gas, say we have tungsten hexafluoride or sulfur hexafluoride, you could pour that gas to the one side of the balloon in this container and pour it to the one side of the balloon, and the balloon will move the opposite way because it moves away from the more dense, because it's helium. So it will move to where the less dense is. So it will move the opposite way to where you pour that gas at the side of it.
So the idea of having side-by-side gases of different densities, and then you put a balloon in there and see which way it goes. Wonderful plan. I love it. I just cannot think of a way to make this work. If you pour a gas, like take a heavy gas and pour it on one side, it's going to just sort of, flow across. Maybe if you're pouring it through a zone and it pours down, you could get it to sort of like go more down than across, and so they're creating like a gradient, a difference in density, like less dense over here, more dense over here, but it's going to be flowing while you do it. You set up like a wind tunnel where you're injecting two different gases side by side and creating a barrier that way. That could probably work, but I mean, I'm not doing that. I don't think it's reasonable to expect anybody's going to do that at home. So if you can come up with a way to actually test that and show that it works, maybe just pouring in the gas, like you'll have a difference in density for a brief moment. Is that enough? And then as the gas flows across, is that going to tell us something? Yeah, I cannot think of a way to make. I just cannot think of a way to make this work. It's a good idea, though. It would really tell us something.
And that's essentially, it's not caused by the acceleration. It's the density. The density's changed areas, and it's changed density in different areas. So then obviously the helium balloon reacts to where the less dense is and where the more dense is.
Okay, I think I'm starting to understand what you're saying, but I need you to clarify for me that this is your position. I don't want to misunderstand you. So please tell me if this is correct. I believe I'm hearing you say that when an object is in a medium, that the variation in density within that medium determines the direction the object will go. So if I have air and the air is denser at the bottom than it is at the top, that Putting a helium balloon in there that is less dense will be driven away from the more dense air up towards the less dense air. And so then when we accelerate the plane, the more dense air packs up on one side, and that more dense air drives the helium balloon sideways away from it. And that is the concept of relative density. Please confirm for me, that is specifically what you mean. The object must be in contact with the medium, and there must be a density variation in that medium that gives us the direction that we go.
So yeah, the plane's just falling faster than what they are, essentially. They're not weightless, they're not floating. It's an illusion, it's a trick of the mind kind of thing. A reference frame, whatever you want to call it. But really, they're still just falling.
Good points all. Yes, the people are not really being pressed into the ceiling. They are just falling slower than the aircraft is falling. Correct. I agree. Is this just an illusion, just a trick of the mind? Yeah, I think in a manner of speaking, that's fair to say. Is it just because of your reference frame? Absolutely, that's the magic word. The reference frame of the camera is falling down with the aircraft, and therefore everything looks to be stationary.
See, he says that it becomes zero then, or the K, I'm guessing, or the weight, or I think he means the K became zero, but I mean, in this sense he's talking about weight, but to me this has nothing at all to do with weight. I mean, if you wanted to measure the weight, I suppose you could stick a scale to the ceiling and then accelerate down faster so that the people lag behind enough so that they touch the ceiling, and then you can measure their weight. They still have weight, they're not weightless, do you know what I mean?
Right, exactly. Let me stop using the word weight. It's too confusing. I'm giving you this one. There's no weight. We're not going to talk about weight. There's a force. If you stuck a scale in the ceiling, would there be a force there between the person pressing against the ceiling? Measure that. That's the number that I'm talking about. That's the W on my slide. I'll change it to an F going forward. We'll make that an F. That's a force.
The vectors for density is pretty much every single vector. It just depends where the density is, and because normally the density all around you is the same, on either side it's less dense above the object.
I'm going to want to disagree with you on that, but maybe we can reword it into something that works. Density is not a vector. Density is mass divided by volume. Mass is not a vector. Volume is not a vector. Therefore, density is not a vector. Density does not have direction, and therefore it is not a vector. We can't simply say density has every direction and that counts. No, every direction means there's no specific direction, right? So that's not going to work. But you could say that the density differential has a direction. You can do that. Math words here. A density gradient. A density gradient can be a vector. That would be a vector. The direction in which the density is increasing, right? So if we say that it's dense over here and less dense over here, then we have a direction from the less dense to the more dense. That could be a vector, and that could be the vector that you're seeking. So the density itself is not the vector, but the difference between two pockets of density can create a vector, and we call that the gradient.
He does, however, come up with a good experiment. I mean, obviously he mentions the balloons in the car, but as I've said, this is essentially the same thing. It's nothing really to do with acceleration, it's just where the density of the medium is. He comes up with an experiment that people can do to measure the angles based on acceleration.
The point about the experiment that was important, but you seem to have maybe missed, is that the angle of the balloon and the angle of the acceleration is exactly the same. Now, is that just a coincidence? If this is not about the acceleration, then why do they match?
Actually, while we're on acceleration, I'd like to talk about the accelerometer. So basically, the accelerometer, you put the accelerometer on the floor. It measures that accelerating at 9.81, whatever, something like that. And basically, if you look at the phone on the floor, your phone's not moving, it's not accelerating. But yet the accelerometer says it's accelerating. Now you drop the accelerometer, it reads 0. But yet it's accelerating. You can see it's accelerating, it's moving, it's accelerating. So that tells me that really the accelerometer is no good, because let's, for instance, say you was in some kind of capsule with no windows, and say you couldn't feel acceleration, you couldn't feel any movement whatsoever. And then let's say you was actually falling out the sky, but you couldn't feel it for whatever reason. Obviously you would in real life, but let's for a minute pretend that you wouldn't feel it. Then that accelerometer is not going to be no of help of you. You're going to think you're stationary when really you are coming crashing to the floor. Because it's saying that you're reading 0 acceleration when you drop it, when you're falling. So again, I think it's just programmed to say that. Because obviously you can clearly see it's accelerating when you drop it. But yeah, that says it's basically stationary, which it's not.
So on the accelerometers, it reads 1G when it's stationary here on the Earth. Yes, it does. Does that mean that it doesn't work? Does that mean that when I rotate my phone, that the axes don't reflect that? Does that mean that if I accelerate the phone, that I don't see it right there on, you can see it too. It works. You can say there's problems with it, and we could talk about what those are. But to say because it does something weird that we can't use this tool, that doesn't seem fair. The tool works, and we know how it works. Do you know how it works? Maybe we should talk about that. Let me know if you want to talk about how this is made to work, but I think it should be enough for us to see that it clearly does work. We can accelerate the phone in any number of ways, and we can look at how the little charts respond to us doing that. And we can measure the acceleration and then measure the rate and see, hey, look, they match. The phone works. With one little exception that you point out, which is that it reports an acceleration. Like right now, it's telling me that someone is accelerating this phone upwards at 1G. And clearly it isn't, right? It isn't. So maybe what it's doing isn't what you expected it to do, or maybe the name accelerometer is a misnomer in some way. Maybe that's not a fair description of what this device does. But the device clearly works. All the theory in the world about relative density or bent space-time is worth nothing if it doesn't match reality. The accelerometer is reality that you can hold in your hand. Let's not dismiss that. What I really want to show is that the acceleration absolutely matters. The acceleration, as shown by the accelerometer on the phone, matches the angle the balloon holds at. Okay? That is not a coincidence. And if you're willing to do the mathematical analysis with me, I can show you exactly why we can take this equation of relative density and we can break it down, and what we will show is that what the phone is saying is affecting the helium balloon, it is affecting the other balloons, it's affecting all things. The reason this falls is the same reason you get 1G on the phone. The phone is measuring the k vector. That is the k vector that is in that equation, is the acceleration on the phone. They match 100%. So I think that's a very important point. Even if we have not established a causal relationship, there is absolutely an undeniable correlation that they match. And this is an experiment that you can do yourself to show that they match. And if you like, we can take it into the mathematics and show why they match. Okay, I had a few questions. Let me hit them. I'll throw them up on a slide or something. Okay, questions specifically for you to answer. 1, what is down? Why down? Why do denser things, when you're not accelerating, dense things go down, light things go up in whatever medium of comparison? Why that way? Your answer so far seems to have been because that's where the denser things are. Why? Why do they do this? And remember my equation, y does the amount of force that rock pulls down with match that formula. It has nothing to do with the difference between the density above it and the density below it. It has to do with the difference between the density of the rock and the density of the water that surrounds the rock, right? Not the difference between the water below and the water above. The difference between the rock and the water predicts that motion, and the amount of force is predicted as well. Okay, so why is that? Next question. Your sideways gases experiment is intriguing. That's really interesting. Can you do that? Can you do that experiment, and can you do it with different gases and different things at different weights? Because if you inject a gas moving sideways, you could do it that way, like release the gas and the gas comes flowing in, there'll be a density difference at the boundary, but there's also a flow that will push things along with it. So, maybe throw some sulfur hexafluoride at a helium balloon and then throw some helium at a sulfur hexafluoride balloon and see if the helium doesn't just blow the thing across in the same way. Or maybe drop the gas downward. I don't know. This does not sound like an easy experiment. I'll keep trying to think about it to see if I can think of anything else. For my part, I've been using the acceleration technique. The acceleration technique works, and I would say we know why it works. And that's a good follow-up question. Are you willing to look at the math for this? I would say F equals ma, right? F equals ma, if we agree on that, and I think that we do, we should be able to say if I'm with the accelerometer measuring accelerations, I've got A. If I've got density and volume, I've got mass. So I should be able to crank out the force from F equals ma. If you're willing to do that math, I am happy to go through it step by step, answer any questions that you have, and show that that is literally my equation of relative density, is F equals ma. That's literally what that equation is. It is nothing more than F equals ma with the difference of density factored out. And then last, the accelerometer. Why are you not willing to accept the results of the accelerometer? It matched the balloon, so whatever it's doing is explaining, or at least matching, the results that we see. So that seems like a really valuable tool that we should not be throwing out. Okay, let me hit the editing room now and see. It'll probably be tomorrow, or actually Friday, before I get this to you.